Hello, welcome to another module in this massive open online course. So we are looking at examples of LTI systems, or we are solving problems related to LTI systems. So let us continue looking at this discussion, that is LTI systems. And we are solving problems. So the problem that I'm currently trying to address is whether this modulation by carrier, that is yt equals xt times cosine 2 pi fct, is this we are trying to address if this is an LTI system. Now to first do that, let us check linearity. Is this a linear system? Remember, for LTI, an LTI system has to be both linear and time invariant. So let us first check linearity. To check linearity, we have to see if it is additive and homogeneous. Okay, so satisfies the additivity and homogeneity properties. So additivity, coming now first to additivity, we have, let's say, t of x1t equals x1t cosine 2 pi fct. This is your y1t. Similarly, t of x2t equals x2t cosine 2 pi fct. This is your y2t. Now t of x1t plus x2t, this is equal to, you can see that is your modulating signal x1t plus x2t times cosine 2 pi fct, which is again x1t cosine 2 pi fct, that is y1t plus x2t cosine 2 pi fct, which is y2t. Okay, so this is t of x1t plus x2t equals y1t plus y2t. That is basically t of x1t plus t of x2t. Okay, so therefore it satisfies the additivity property. Okay, therefore it satisfies the additivity property. Okay, so we have seen that it satisfies the additivity property. Now how about the other property in linearity is homogeneity. Alright, so we have to check if it satisfies the homogeneity property. So what we want to check next is homogeneity. So let's say again t of xt equals xt cosine 2 pi fct. Now t of alpha, so this is your yt, t T of alpha times xt, naturally this is equal to alpha times xt cosine 2 pi fct, which you can clearly see is alpha times yt, which is basically alpha times t of xt. Therefore, system is again t of alpha times xt is alpha times t of xt. Therefore, system satisfies homogeneity property. Okay. Therefore, system satisfies homogeneity. So, you have additivity, homogeneity. So, system satisfies both additivity and homogeneity properties. Therefore, the system is linear. So, the modulator, the modulation system is a linear system. Therefore, since additivity plus homogeneity, system is linear. It is a linear system. Now, how about time invariance? Is it time invariant? How about the time invariance property? To address that, let us look at t of xt, that is equal to xt cosine 2 pi fct. This is your yt. Now, for time invariance, we have to consider a delayed input or shifted input, x of t minus t naught. This is your delayed input. This is equal to x of t minus t naught into cosine 2 pi fct. And now you see you have a problem here. This is not equal to y of t minus t naught, where y of t minus t naught you can see is x of t minus t naught into cosine 2 pi fc t minus t naught. So, that is the problem. What you can see here is that, interestingly, t of x of t minus t naught is not equal to y of t minus t naught. That is, if you delay the input, the resulting output is not the output corresponding to the previous input, that is not the output corresponding to xt delayed. Similarly, these two things are different, that is t of xt minus t naught is not equal to y of t minus t naught. Therefore, the system is not time invariant. That is an important observation. Therefore, hence it is not an LTI system, because system is LTI only if it is both linear and time invariant. The system is linear but not time invariant, hence it is not an LTI system. It is linear but not time invariant, hence the modulation operation or modulator subsystem is not not a linear time invariant system. This is not an LTI system. Okay, so that is the important aspect that you have to understand. Sometimes it's not obvious, so it's a linear system, but it's not a time invariant system. All right. And let us do one final example to understand something. So let us do another final example for an LTI system, or consider, let the transformation represent let this represent an LTI system. Now, for this, if this represents an LTI system, then show that T of e to the power of j 2 pi f naught t for any frequency f naught equals, that is, if you consider any input which is a complex sinusoid, and this is a very interesting property, for a complex sinusoid, the output is some constant c times e to the power of j 2 pi f naught t, and this is a very interesting property, that is basically output to any complex, that is, if you consider an LTI system, output, if the input is a complex sinusoid, the output is also a complex sinusoid, simply scaled by another constant c, and this is a very interesting result. Output is a complex sinusoid, scaled by c, where c equals this c equals a constant, and input is a complex sinusoid, then output is also a complex sinusoid scaled by c. This can be shown as follows. Since we have, let t e to the power of j 2 pi f naught t, let this be equal to yt. Okay. Since LTI, since the system is shown to be LTI, it is a linear time invariant system, this implies t e to the power of j 2 pi f t minus t naught equals y of t minus t naught, but t e to the power of j 2 pi f t minus t naught, this is equal to t e to the power of j 2 pi f t e to the power of minus j 2 pi e to the power of minus j 2 pi f naught t naught, which is equal to y of t minus t naught. Now, look at this, e to the power of minus j 2 pi f naught t naught, this is simply a scaling factor, because f naught is a constant, t naught, the delay, is a constant, I mean we are assuming. So, this is simply a scaling factor. You can see this is similar to your scaling factor alpha. So, using now homogeneity, this implies from LTI, this implies e to the power of minus j 2 pi f naught t naught into t of e to the power of j 2 pi f naught t equals y of t minus t naught, but t to the power of, but t e to the power of j 2 pi f naught t, this is nothing but y of t. Okay. So, what we have, okay, so this is y of t. So, what we have is basically, this implies y of t into e to the power of minus j 2 pi f naught t naught equals y of t minus t naught, and this holds for all t naught. Of course, this holds for all t comma t naught. Now set t equal to 0 and t naught equals minus t. This implies y of 0 e to the power of minus j 2 pi f naught t is equal to, so we are setting t naught equal to minus t e to the power of j 2 pi f naught t equals y of t. So what we have been able to show is that y of t equals now this is y naught, you can call this as your constant c. So what we have shown is that y of t, this implies y of t equals some constant c e to the power of j 2 pi f naught t. Okay, so output is simply scaled version of input. That is this shows if input equals e to the power of j 2 pi f naught t, output equals some constant factor times the input. So output is simply some constant times the input. Such an input is known as an eigenfunction. So e to the power of j 2 pi f naught t is an eigenfunction of the LTI system, because the output is simply a scaled version of the input. Hence this implies, there is a very interesting property, this implies e to the power of j 2 pi f naught t is an eigenfunction. This is a very interesting property. Is an eigenfunction of an LTI system, for that matter is an eigenfunction of any LTI system. Okay, e to the power of j 2 pi f naught t. This has a very special relevance. Of course, we are going to explore it further through the various modules, but it's important to realize that this function, this complex sinusoid, has very important relevance, correct, in the context of analysis of LTI systems, because this is an eigenfunction of any LTI system. All right. So with that, we'll wrap up our example section. So hopefully we have done several examples which have hopefully to some extent have covered various aspects of the principles of signals and systems, or the various introductory principles of signals and systems, classification of signals and systems that we have seen so far, and we will look at other aspects in the subsequent modules.